My presentation title today is actually Advanced Computational Material Synthesis Approach for Fire Resilience Building Materials. So I left off the building material because the title would be too long, because the technique itself can be applied to any material, so it does not limit it to just fire resilience material. But we normally work on flame retardants, so that's why we started on flame retardants. So I'll introduce myself again. I'm Anthony Chun Yin Yuen, and I'm an assistant professor here, newly joined. But I would like to give acknowledgement to Dr. Timothy Chen from UNSW, my colleague, Mr. Ivan Cordero, my PhD student at UNSW, and Mr. Enzo Chen sitting over there, also my PhD student, and also Joe next to him, also from UNSW. But now we are locating in Hong Kong at City University of Hong Kong. So here's the presentation outline. So on the right, there's sort of like the framework of what we do in brief. But to talk about it, we will give you some background and the motivation of our research. And unfortunately, I need to talk about some theory behind the molecular dynamics, because all my research is revolving around MD itself. And because we are working on fire simulation, so unavoidably, we need to look into pyrolysis, especially the solid degradation and the gas decomposition component. I will welcome any questions afterwards, but after that, we will also sort of like try to identify the key flame retardant mechanism. And believe it or not, you can actually do it in MD, and you can visualize it in an atomic sense. But I will talk more about it later. And more importantly is, how do we link all these reviewed information into our fire simulation and more practical studies, which on the right bottom figure, you can see how can we actually model a fire that represent the material that we study through the MD. And of course, I would talk about some future work and applications. So when I was in Australia, the cladding fire issue has been a big problem because of the Grenfell Tower incident in UK. And that's how we get a large theme-based research center, namely the ARC Training Center in Fire Safety. And our training center, where me, Enzo, and Joe used to work in, we work very hard on studying flame retardant materials. But along the way, when we are studying like cladding facades, such as, like the outer walls of the McDonald's, and so forth, and even some of the new residential building, you have external wall cladding system covering the building. We find that, well, firstly, they're mainly made of aluminium cladding panels, and within it's normally some polymers which are easily flammable. And the reason why they do it is because of the lightweight and easy to install properties. But little do they know, when they design that, it is highly flammable. And not only that, when it caught on flame, it sort of like engulfed the whole building. So it makes the evacuation process super hard to execute. So when we design our flame retardant, unfortunately, for different specific polymer, there's demanding of different variation of chemical formulas. So we need to dig into a bit of the chemistry. So it is essential to understand the chemistry behind. But we, as mechanical engineer, or from civil engineering, we sort of a bit lacking in that sense. So we sort of like to discover our own way of strengthen up the understanding from a mechanical sense. So that's the reason why we start looking at molecular dynamics. So Well, in terms of experiment, you guys may already know it is conveniently use the TGA or the thermogravimetric analyzer coupled with FTIR system to review the thermal degradation rate. As you can see on the right-hand curve, FTIR will further assist you for the spectrometry to look into the gas as well. Not only that, you can look into a combustible environment and a flaming environment via the cone calorimeter. So these are the two sort of like benchtop tests that people commonly use to study any flammability and the thermal stability of any polymer materials. So that's worth mentioning. So if you look into the flaming of the material itself, it's actually involving a lot more than it looks, because not only it goes through the pyrolysis process, sometimes if the material is a thermoplastic, it melts as well, so it has a molten phase. And of course, this molten phase will further gasify into gas, and gas phase is where we are interested in terms of our simulation, is because combustion occurs when gas volatile is oxidized and ignited. Because, you know, if you look at the phi triangle, you always need the heat, the oxidizing agent, and so forth. And to design our model, we need to look into 6 essential components here when we are really studying the sort of surface regretting a polymer degradation effect. So and another important thing to mention here is not only the material degrades. If you flame retardant material, very often you will formulate a char layer. So it's also important to have a surface tracking model that is able to mimic the layer of the char. So I will further mention about that later, but more importantly is there are 5 phenomena that we need to address before we fully understand the whole picture of the flaming process of any building materials. So to bridge the gap of understanding that we missed out, more importantly is the pyrolysis behavior. We as a group, we are the first sponge to introduce the molecular dynamics involving the reactive force field. It is very common in MD to have that. To actually base on building a molecular structure in a cube type of way, and then we adding heat into the control volume, and then we see how the molecule break down on the right hand side. So in this section, we were going to give you a brief understanding by having a benchmark study on polyethylene PMMA, utilize this MD technique. So we will mention how to actually study the so-called or characterize the degradation rate of this molecule. But before that, as I mentioned, we have to dig into some background theory. But in short, MD is essentially based on Newton's second law. In essence, F equals ma. So what it does is based on the evaluation of the forces, mainly governed by the energy. You can see on the right-hand side, there's a flow chart. But on the left, if you are familiar with the evacuation model, it's similar to the agent-based model where your particle is influenced by the force field, and then it moves around based on the evaluated force for each iteration steps. Of course, there's a lot of force that governs the movement of a particle, like you have the van der Waals, the electrostatic. So if you look at the right-hand figure, then you will find that on the left part, you have your van der Waals, the polarization. So what it does is through the provided Reacts FF reaction table for a specified set of elements. So say if we pick C, H, and O, then we iterate through the energy. And then once we solve it, we solve the bond order and bond angle to govern whether this is a single bond, this is a double bond, or so forth. Once we decide that, then we can iterate through the steps and conclude whether a breakage will occur or a bonding will occur based on the evaluation. So the other thing is initialization of the simulation. We need to start off with somewhere for any simulation. So first step is we need to know what we are studying. So in this case, say for example, we pick this monomer unit, normally come in a chain form, and then you can propagate the same chain to formulate a linear long polymer chain. Once you do that, you can now formulate the amorphous system through compression on a large volume to a specified volume based on the density you desire. So this is very similar to any chemical process to formulate like high density polyethylene, for example. This is called the annealing process. So repeating that, because simulation, there's no cost of doing so. So we can hypothetically do it for polyethylene, PMMA, polystyrene, so forth. So the next steps is once we formulate the molecular structure based on the monomer. So you can see PE is essentially C2H4 and then propagating. And I am not very sure about PMMA. It's a bit more complex, but in short, you can look at the structure in this figure here. Polystyrene is with a benzene ring on top, but similar to the polyethylene. Of course, with more elements, the density would be sort of a bit higher compared to the other two. But anyway, that's not the main focus. So here, once we formulate this structure, we put it into a sort of like a heating chamber condition. So you apply heat to each of the atoms within the system. So this temperature, 280 ranging to 4,000, is actually much higher than the TGA temperature. Many people may argue that, but we need to also understand that the scale of the simulation is different in MD because we are running in pittosecond, which is like 10 to the minus 12. So the temperature needs to be higher to speed up the process of the molecular breakdown. But some will argue, like, how do you then validate your simulation data? Is we are quantifying a kinetic rate, which is dimensionless. Its value works for various time and dimensions. So normally that works for most of the case, and that's how we validate our data. But regardless, here is a sample for the polyethylene breakdown. Like you can see from the beginning of the simulation, it looks stable. And then once you exert heat to the atom, it starts to degrade and some gas volatile will form and flow across the simulation flow field. And you can see eventually there's more breakage occur, and then you can start monitoring the gas species formulated inside this volume. So we did a benchmark comparison between the three polymers, and you can see the spectrum. So a good thing about this gas decomposition is we can even benchmark against FTIR results to see whether the major gas are formed and whether they correlate to each other to see whether if we are solving a more complex material, then whether they comply to each other. So here's sort of like a characterization of the kinetics rate. We look into the pyrolysis behavior. The importance of having this rate is, if you're familiar with FDS, then you always need the above Arrhenius expression to solve the kinetic rate of your pyrolysis. And in molecular dynamics, you extract this value by having a few different temperature heating rates, similar to your TGA. So say if we have 4 different points, then we can do a linear interpolation to acquire the slope. Then we can convert them into pre-exponential factor A and activation energy E, and then to formulate our hypothetical pyrolysis rate based on the result we extracted from ND. So there are a few ways to trace this rate. For very common and easily well-known polymers, we can just look into their monomer structure, the carbon number. However, for some of the more complex material, then we trace the molecular weight of the main bulk of the material. So we look into the rate of this curve here to trace the drop in the molecular weight. Anyway, so here's the result for HDPE, PMMA, and PS. So you can see for simple polymer structure, the result is agreeing quite well with the experimental rate against say 273.25 for activation energy for HDPE against 266.74. So it's around just maybe 5 to 10% off, but it's pretty good in terms of the accuracy. Of course, for more complex formula such as PMMA, it's the degree of error is a bit higher, but it's still tolerable because we are still looking at the polymer itself. We haven't involved the flame retardant yet. When the flame retardant come into the matrix, it will cause the system to look way more complex than this. But I would say for the polymer, if we just look at the polymer itself, it's pretty accurate. So after we confirm that this technique works for the degradation for any generic polymers that we want to study, we start to play around with the simulation to put in more different chemicals into the matrix of the system to study whether the material we added is effective as a flame retardant. And over time, we identify a few key behaviors that we find that is worthwhile mentioning that will support like our explanation of why some materials are better flame retardants than the others. But most of the case, the main effect of fireproofing a material is the charring effect. So charring is like carbonaceous atom forming at the surface of a polymer. So what it does is not only by itself, it's not very heat penetrative. So it protects the inside material from burning by acting as a protective layer itself. So the first two sort of work hand to hand to each other. But we did some other study like involving Intumescent char, which will also cause the polymer material to char and expand even. And it gives a bit better protection to the material. And we call that like a synergistic effect. But anyway, so the physical protection could be due to char or could be due to the formulation of a thin layer that actually is not penetrative with heat. And the dilution and the chemical effect is more of the reduction in oxygen. So there's some material that will capture fuel and oxygen. So it's like a radical capturing effect. So once you take away the major component of the fire triangle, then you won't have as much fire as you anticipate. And you also have the reduction in chemical reaction, but I guess I will mention that further in a case example. So we started off with working on HDPE, just hypothetically looking with APP, which is ammonia polyphosphate. And as you may know, all phosphorus compounds are very effective, but the question is why and how does it fireproof the polyethylene? So you can see we formulate two polymers, one with and one without the APP. And then what we do is we replicate the same process and we benchmark the carbon atom for HDPE and HDPE/APP. And you can see the number of carbonaceous atom remain in the system for the APP is version is way more than the HDPE, and that's a sign of there's more charring occur in the HDPE system. So that's just one example, but here there's more recent work on some more commonly applied materials in our daily life. For example, epoxy resin. We all know that epoxy is very popular because of its biodegradability, environmental friendliness, and so forth. And it has been commonly applied in like floorings, coating on woods to protect the wood from oxidizing. And I think nowadays it's very commonly found for any surface. You have epoxy coating layers. But again, the problem lies in the flammability of epoxy itself. So we try to understand the flammability first of epoxy by doing a very simple study. But first, in the MD simulation, we need to replicate the chemical process to formulate the epoxy structure itself. So you need the basic component on your left. You need the hardener and then the cross-linker. So what the cross-linker does is it links up these two components here, and then it formulates the chain structure. And then again, we do the amorphous structure formulating process to formulate this nice epoxy here. So what we can do here as well is, again, benchmark this structure with and without flame retardant. But this time we select a so-called activated carbon. So the reason behind this is because one of my students, she discovered this carbonized peanut shell structure, which is similar to a graphene type of structure. But what is so advantageous is we can just use a natural material like peanut shell, burn it, and then we can acquire this carbonaceous structure that is very good at the charring. And of course, with some binders and some linkers like melamine and phytic acid commonly extracted from the Intumescent formula, we can derive a combination that works tremendously well with the epoxy. And this has been proven from the below literature. Anyway, so if we compare the FTIR result against what we discover in the MD, so what we can do in MD is also trace all the essential components such as your H2, the carbon 1 chain group, carbon 3, and so forth, water, you know. What we can do is we benchmark against the FTIR spectrum and see whether the significance of these compounds are actually occurring within our MD to see if what we are modeling are correct or not. But here I want to stress is the aromatics formation. It is very important to study that as well because it's the precursor of the formation of soot particles. which is the main reason why smoke is formed. Anyway, so through our study, we can find that even in a numerical simulation perspective, by having the incorporation of the flame retardant, it increases the water vapor formation. So this actually contributes to the effect of reducing the chemical reaction that I mentioned in part 4, as well as the capturing of oxygen. So because it forms H2O, it reduces the amount of oxidizer that reacts with the epoxy itself. So you have less reaction, you have less CO at the same time, and you have reduction in the hydrocarbon, which is also always an advantage, because mainly what it burns in the system of the epoxy is the hydrocarbons. So if you remove a lot of them, then you will have much lesser of the combustion to occur. So through this study, we trace the carbon chain C3 plus material, because the gas species sometimes it cannot escape from the computational domain, and it will cause large char residue prediction from ND simulation. But here we propose a technique to overcome this limitation. Is if we want to trace just the char layer itself, and we are only interested in the carbonaceous particle and the chain, we can do a sort of a removal technique periodically. So the concept is simple. So over, say, each 100 iteration, we take away the unnecessary gas species that is not explaining the char layer. And whenever the polymer breaks and some irrelevant compound formulates, we take away them until it's only remain with the char layer itself. So this is a proven technique in the MD world by other colleagues, and we are just utilizing it to study the char capability of materials, and we find it pretty accurate in terms of predicting the char layer thickness. But anyway, more importantly is to predict the intumescent behavior of a charring material. So as we may already learn, the intumescent coating has been long developed and well received as a very effective formula to protect any substrate, basically. So in short, like the intumescent system is just involving like a specific combination like melamine, PER, phosphoric acid, and so forth. There's minor tweaks here and there, but the concept is always similar. You have an acidic component, you have your melamine and your PER, and sometimes you put in the graphene oxide as a rapid charring agent as well. But then the beauty of this formulation is not only it formulates this nice char layer on top, it will expand. On the right hand figure, you see the char layer, when more heat is exerting, the underneath material will work with the flame retardant and expand in char layer. So a part of the polymer or the substrate that is working with the flame retardant somehow contributes to the charring effect. So this is the beauty of the intumescent system. So it couples with the polymer. But looking at the simulation just by the neat polymer itself, as I mentioned, here are the primary and secondary species which are important to study, because we all know methane, propane, or even ethylene are very highly flammable in terms of the combustion process. So if we benchmark this against a HDPE system with PA and PER alone, This is just a part of the formulation of the Intumescent. You can see the formulation of the primary and secondary species changes a lot. So one thing I want to highlight here is the significant formation of H2O and CH2. So, you know, this two formulation alone will limit the flammability of this substrate itself because of the reduction in the chemical reaction and the free radical capturing effect alone. This is not even talking about charring yet. And the reason behind why this is so good is because of the phosphorus-based agent. So it is actually act as a blowing agent formulating the H2O. You can see there's multiple pathway we identify through MD that this phosphoric acid can contribute towards the formulation of H2O. So not only there's one variation, there's actually 4 iterations, different ways to force the gas species that are degraded outside the matrix to form H2O itself. Again, there's more radical scavenging effect that reduce the amount of combustible gas volatile from forming. So you can see there's H2 forming, there's H2O, and then it contributes back to the PO and PO2 itself, which can repeat the chemical process for this radical scavenging effect. So we call the interruption and the slowdown of the flaming process, flame inhibition. And this has been talked about many times in the flame retardant world, but no one has actually given explanation or in terms of the theoretical understanding why this is happening. But maybe this could be a beginning of an answer to that. So if we look into the whole spectrum of the simulation, you can see most importantly is the reduction of the hydrocarbon formation, introducing the flame retardants. So basically, in short, that's what we did in terms of the Intumescent system, and it's still an ongoing project because we are aiming quite high. But today, I would just like to share a part of it. Anyway, so this is more practical now, how we got to link the molecular dynamics simulation into our actual fire simulation studies. For example, FDS or ANSYS Fluent or whatever. So here I demonstrate you a framework in ANSYS Fluent, how we do it. So again, we do a similar process, but this time HDPE with graphene oxide. The reason behind graphene oxide is because it's easily accessible and it works pretty well with HDPE. And again, after the annealing process, we can now study and benchmark the burning behavior of HDPE against HDPE with GO. And looking at this curve itself, we can already confirm that it's pretty similar to the TGA curve for the two materials. But of course, your axis is time instead of like the temperature. But you can see putting in the graphene oxide will prolong the degradation for quite a bit because of the slowing down effect of the charring. So then the question lies in how do we utilize this information to formulate our fire simulation model kinetics. First thing first, if we utilize the Arrhenius expression format, then we can sort of like identify the reaction rates of occurring reactions that contributes towards the pyrolysis process. But then there could be multiple. There could be like 4 to 5 reactions per polymer especially when you add flame retardant into it, it changes the dynamics of the pyrolysis process. So that's why we need more complicated algorithms to trace all the reaction and to curve fit the curve in the MD degradation. So here we propose the genetic-based algorithm to basically assist you automatically to solve all the exponential factors and the activation energy. So the idea is simple. You start off with 2 sets of data, you populate it, and then over time you benchmark against the MD data, see which one best fit. Within 5%, we confirm that is the answer. And then we can do the fire simulation. So here are the results. If we compare how accurate it is for the genetic-based algorithm extracted data for the thermal degradation rate against the data, and you can see it's almost pinpoint. However, now we sort out the reaction rate for the degradation process. Then you may ask, like, what are the other essential models that we need to develop to formulate the simulation framework? So because not only we have pyrolysis, we also have combustion, soot formation, gas species, volatile formation, and so forth. And even the radiation will contribute back to the pyrolysis rate. So how are we going to do so? So as mentioned, first, the solid regression model, we need to couple it back to the reaction rate that can utilize the Arrhenius expression extracted constants that we just did. So conveniently, we can just put it in any generic pyrolysis model, like the heat conduction 1D model to govern the burning of the material. But we spend all this effort to study or review all the very detailed, complex chemical compound that formulates. So it will be advantageous if we do the same way in the combustion side. So that's why we propose using detailed chemistry, and conveniently is available in some commercial software such as ChemKin. So you can use ChemKin to generate the kinetics by using the GRI Mac 3.0, say, for example. It has like already considered 325 reaction and 42 chemical species. And some of them are pretty essential, such as the CO, hydrogen cyanide, and so forth, which are major toxic compounds that we want to study in a fire environment. So not only that, we study some of the precursor for the soot particle formation process. So if you want to accurately model soot, you have to model some essential compounds like acetylene, C2H2, and the ring aromatics formation, the CSH6, CSH5, and so forth, because it contributes to the nucleation and the agglomeration effect of the particle. And there's existing empirical formulas that governs these effects. On the left-hand side, you can see nucleation, coagulation contributes to the number of soot particles, and then your oxidation will reduce the mass of the soot particle. And that's, in short, how it works. So putting all the things together in a framework that can utilize all this model, we then are able to predict the whole spectrum of the 5 phenomena. And not only that, we can couple all the review information in MD in all these modeling components to sort of like represent the material that we study. So I give you this example of the high density polyethylene graphene oxide. So here it's worth mentioning the combustion process, the beginning, the precursor. Normally we set some, say for example in FDS, you can just preset, if you know this is say methane, it will be CH4 kinetics. But then if you just look at any generic fuels like natural gas, it's not all just CH4, there's other components in it. So the way we do it is, on the left hand side, we review the sort of the initial condition, the breakdown of all the species that we review for any molecule based on MD, and then we insert this information to CFD as a start to start off the combustion process. So you can see the flame-led profile we generated already incorporated the MD information to begin with. So by doing so, we find that the accuracy of the result for the cone calorimeter prediction is very accurate in terms of heat release rate. And even the total heat release is in pretty good agreement with the experiment. And if you look at the flame, it is actually even better looking at the whole animation, because you can see at the beginning, HDPE burns at a very earlier stage in comparison to the flame retardant. And then even though the flame retardant HDPE will burn, it gives you a much smaller flame in comparison to the taller flame at 120 seconds. And ultimately, because the HDPE burns at an earlier stage, it consumes the whole material at an earlier stage, so it extinguishes a bit earlier. But the good thing about the flame retardant HDPE is it gives you a very low total heat release rate as a whole. But one thing that we always cannot study in, say, generic code like FDS is the toxicity formation. So what we can deliver on top of the just heat release rate is looking at, like, say, isometric contour plots of something like carbon monoxide, you know. So you can see the reduction of CO by introducing this flame retardant. And we strongly believe the effect of charring plays the most significant role on the reduction of these gas species, because you can see on the right-hand side, if you incorporate the graphene oxide, a very thick char layer has been formed. And this char layer will play a big role in terms of the reduction in flame because of the protection effect. And it will cause more gas volatile to form carbonaceous compound instead of going to combustible volatiles. So in concluding remarks, we have derived the nature materials, and we try to incorporate into a flame retardant. So what we do is not only we study flame retardant, we try to extract bio-inspired materials such as peanut shell, prawn shell, phytic acid, which is commonly extracted in your daily life, to convert it into flame retardant. Of course, they are not like 100% effective, and you need to combine it with some other materials to functionalize it. So that's why we always need to formulate this advanced functional flame retardant by combining the organic material with some inorganic material that is more effective. To date, I can easily answer you. There's still no purely bio-inspired material which are super effective as a flame retardant by itself. But hopefully with the assistance of MD, someday we can develop that. So we have gone through today's lecture that MD can characterize the atomic structure for many advantage of understanding of the flame retardant mechanism, and some interfacial science even, like the oxidation, charring, etching, and so forth. And not only we can characterize, we can even use that as useful input in CFD to predict the fire for building polymers. So I just quickly go through some of our future works. So one of the strengths of our training center is the development of 2D material. And here we present you the Ti3C2 nano sheet. And we can even go as far as the SENTM image to show that it's actually less than 1 nanometer, almost 1 nanometer thick. So that's why it is super effective. So because this nano sheet, not only it can be a very thin protective layer, it can disperse heat away when there's heat penetration. So you can see it's one of the more better materials. If you look at the right-hand side heat release rate curve, so you can see just a few bilayers of Mxene can reduce the heat by like 50% or more. And obviously, I mentioned this because we are performing molecular dynamics on it to be the first group of people to characterize the Mxene itself. So I would say it is very difficult because MD is always driven by the reaction force field. And as of up to date, there's no very workable force field for titanium because Mxene is at least this variation of Mxene is heavily based on titanium, and the reaction force field for titanium is not that reliable at the moment. So what we need to do here is to train our force field to better fit with our case study. So what we discover is the DFT theorem to train our force field. So DFT essentially is to make sure the bond angle, bond order, and the bonding energy are theoretically correct. So because it's based on first principle, if we fulfill the DFT theorem, then we can sort of train the force field to better cope with the simulation behavior we wanted. And of course, otherwise, it's just by experience because we know that the Mxene sheet doesn't break easily. So whenever we see it breaks, we know that it's already not working. So here's where we're up to. It's not doing very bad. We managed to maintain the Mxene sheet shape through the right-hand side simulation. And you can see it prolongs the thermal degradation process for quite a bit. And again, the Mxene behavior, the flame retardant mechanism is way more complex because not only it assists in the char formation, it remains with just TiO2, which is by itself a very good flame retardant as well, because TiO2 itself can act as a crystalline layer, as a thermal and physical barrier by itself. So I hope I give you some insight about simulation and some understanding through this presentation. Thank you all for sitting. Now will be the Q&A section. Thank you very much.